This video is going to explain how to prove triangles similar and also go over some basics on similarity. So there are three ways to prove triangles are similar. We have the angle-angle similarity theorem, the side-angle-side similarity theorem, and the side-side-side similarity theorem. The difference between this side-angle-side and the side-side-side and what we did before with congruency theorems is that here our sides don't have to be congruent, they have to be proportional, okay? So the big takeaways here for similarity is that when you have similar triangles or similar polygons, any figure that's similar to another one, your angles, your corresponding angles will be congruent and your corresponding sides are proportional. If our corresponding sides were congruent, then the figures would be congruent. Let's take a closer look at one of these theorems. We're going to take a look at all of them. Let's start with angle-angle similarity. I am given two triangles. I'm given sort of the outside triangle here and then the smaller triangle that's inside it, and I'm asked, are they similar? So I know I'm going with angle-angle similarity, so you can probably guess I'm not given anything about the sides. I don't really care about the sides. I just need to show that the angles are congruent. So this symbol here means that those lines are parallel. Parallel lines are really helpful in helping to determine if angles are congruent because we can use our angle pair relationships. In this case, I can take sort of AB and DE and think about those as my parallel lines, and then I can think about these each as a transversal. So I have this transversal from A to C and this transversal from B to C. Okay, so all I did here is sort of redraw this in a more familiar way, how we're more familiar with seeing angle pair relationships. Now, I can connect angle A with angle EDC, these two right here, and if I ignore this transversal for a second, I can see that those are corresponding angles. So I'm not sure what the measure of them is, but that actually doesn't matter, because all I need to show is that two angles are congruent, not that they measure a certain amount. I can do the same thing over here with this transversal. So now if I ignore that transversal there, I can see I did the exact same thing using corresponding angles. So that would respond with this one and this one down here. I gave these ones two tick marks, two arcs, rather than one because I don't know if these have the same measure. All I know is that B and DEC are congruent, and that these two are congruent. I don't know that these ones are congruent to each other. So from here, I can ask myself, are these triangles similar? And it might help for you to redraw these triangles separate from each other, because then you could really clearly see that we have two triangles, okay? This is my big one, this is my small one. In my big triangle here, I have an angle up here with 1 and an angle up here with 2. In my small triangle, same thing. From here, I can say, yes, I have two corresponding congruent angles. In fact, because this angle DCE is in both triangles, this is the same angle by the reflexive property, I actually know information about all three angles, but I don't even need it because I just need two corresponding angles. So, because I have two corresponding angles that are congruent, these two triangles are similar. I can write a similarity statement. I can write that triangle ABC is similar, that's my symbol for similar, is similar to triangle, and the one that goes with A, I look for the one arc D. B, E, and C, again, reflexive property is the same. So that's how I can use angle-angle similarity to prove that two triangles are similar. Now let's take a look at side-angle-side similarity. So for side-angle-side, you will be given two sides for each triangle. If you don't have that much information, maybe you're looking at a figure that looks like this and you're only giving 3 values, you don't have enough information. So try to avoid this one. You need to be given at least 4 of the 6 sides of the triangles. So, side, angle, side. For side, angle, side, I need two sides and the angle between them. Those sides have to be proportional and the angles need to be congruent. So I'm not given any angles from just looking at the drawing, but I can, I don't have any arcs or I don't have any measures, but I can look at this and I can identify where there are congruent angles. So I can use the verticals angles theorem to say that I know that this angle here needs to be congruent to that angle there. Now I have a side, an angle, and a side for my smaller triangle, and for my bigger triangle I have side, angle, side. Okay, so we're in business. I'm given the information, but before I can just assume that they're similar, I need to check and make sure that the sides are proportional. So how do I set up a proportion? If I want to check that the sides are proportional, what I need to do is set up fractions. And here I know I'm going to have two sets of proportions, one for one pair of corresponding sides and one for the second pair of corresponding sides. So I know I'm going to get two fractions, and I know that if they are similar, these fractions will be equal to each other. Okay? Fraction, proportion, ratio, it's all sort of the same. So I want to set up some sort of way to relate the sides of these two triangles. And I'm going to do that through turning them into fractions. I'm going to say my smaller side of my little triangle, and that's going to be proportional to my smaller side of my bigger triangle. Now, I've used my smaller sides, but I still have this bigger side that's given. I have the bigger side of my smaller triangle is going, and I'm going to put that over my bigger side of my bigger triangle, and I'm going to test to see if these two fractions, or these two ratios, are proportional. I know that they'll be proportional if they can reduce to the same thing. Okay? So, some fancy terminology that I'm not going to bother you with is sort of, these are the corresponding sides, my 2 and my 6, my 3 and my 9. But really the most important thing is if you put your two smaller numbers together, put your two bigger numbers together. So my smallest number of my small triangle needs to go with my smaller number of my bigger triangle, right? So for each triangle, I'm given a smaller and a bigger number, and I just got to match them. That's really just the easiest way to think about it. Now, 2/6. I can divide both of my denominator and my numerator by 2, and I would end up with 1/3. For 3/9, I can divide my numerator and my denominator by 3. 3 is a common factor, and if I divide them by 3, I will end up with 1/3. This works, okay? These two are similar because they are proportional. They're fractions reduced to the same thing. All right, let's take a look at the last way to prove that triangles are similar. And honestly, this is the easiest one. Side-side-side similarity. The only thing you need to do here is test to make sure that all of the corresponding sides are proportional, just like we did in the last one. You don't have to find any angles, you don't need to use angle pair relationships, nothing about angles here, just sides. So, let's say I am buying toy sailboats for 2 children. One is a very small child, one is more of a toddler. So I want 2 different size sailboats. Now, I need to see, are they dilation? Is it a shrink? Did I enlarge it? Are they similar? Is the size of the sail proportional? Okay, are they similar? Same shape, but different size. So, I'm going to test this the exact same way I tested my 2 sides for side angle side. You need to set up proportions. You need to turn these numbers into something you can work with, and that again is going to look like fractions, and you're going to reduce each one to test if they reduce to the same thing. So, I know I'm going to end up with 3 fractions this time. The reason why I'm ending up with 3 here, but I had 2 in the last one, is in the last one I was only given 2 sets of corresponding sides. Here I'm given all the sides, which a triangle has 3 sides. So 3 sets of corresponding sides. And I know that they'll be equal if they're similar. So I'm going to put equal signs here, but really that's what we're testing to see. I don't know if they're equal yet. I take my smallest number in my small. I put that on top of my smallest number in my bigger sailboat. If you put the bigger sailboat as the numerator and the smaller sailboat as the denominator, that's totally fine. All that matters is that all of your numerators are from one triangle and all your denominators are from another triangle. The other triangle. You only have 2 here. So 1 goes with 4. Let's put in my middle number, 1.5. And 1.5 is going to match up with 6. If this sailboat was spun around or upside down or something like that, don't be fooled. Here it's nice and easy because I got my bottoms, I got my left sides, and I got my right sides of the triangle. But if it weren't that way, just match it up. Your smallest number is going to go with your smallest number. Your medium on one triangle is going to go with your medium on another. Okay, and my biggest, which is 2 for my small triangle, it's going to go with my biggest, which is 8 for my bigger triangle. Now I need to test this. 1/4. Can't reduce it. Let's leave it like that. 2/8. That one's pretty easy to reduce. I can divide my numerator and denominator by 2, and I will get 1/4. So far those ones work, but all 3 have to work. 1.5 and 6. It's hard when you have decimals. I could plug this into a calculator if I had one. 1.5 divided by 6, and I could see if I got 1/4, which is the same as 0.25. I could also say to myself 1.5. Okay, for here, I know I need to, to get from 1 to 4, I had to multiply my numerator times 4 to get the denominator. Same here. Take your numerator times 4 to get to the denominator. So if I look at this bottom part of my sail, I have to multiply that by 4 to get the bottom of this sail. This side, I have to multiply by 4 to get to this side. So let's test. If I multiply 1.5 times 4, am I going to get 6? Okay? 1.5 times 4. So let me think. What's 1.5 times 2? I'm going to get 1.5 times 2 is 3. Now that I've multiplied by 2, I just need to multiply by 2 again. 3 times 2 is 6. So yes, this does reduce to 1/4. Because these all reduce to the same fraction, the same ratio, they are proportional. Okay? So, let's write a triangle similarity statement. If I have triangle BOA, that is going to be similar here to triangle. The one that matches up with B is T. The one that matches up with O is going to be I. And the one that matches up with A is going to be N. BOA, triangle BOA is similar to triangle TIN. And we're going boatin'. So far we've been talking about similar triangles, and they're a little bit special. So I want to sort of zoom out for a second and talk about similar polygons in general. So a polygon is any shape that has straight sides, no curves, we don't have any overlapping sides, pretty much any shape you think of. Think about the 2-dimensional shapes on your reference sheet. Those are polygons. So for polygons that are similar, again, we have all the corresponding angles are congruent and the corresponding sides are proportional. That is going to be true. That's true for triangles for every shape. Now let's take a look at regular polygons. Remember, a regular polygon is a polygon where all the interior angles are congruent and all of the sides are congruent. So, here I have a square. That's a regular polygon, a regular quadrilateral. Here is a regular pentagon, and here is a regular hexagon. I gave away the trick here, in that regular polygons are always similar to each other. So all squares will be similar to each other. All regular pentagons will be similar to each other because all of those angles are congruent and all of the sides are going to be proportional because let's say I have another square that's bigger than this one. Let's say that the length of this side is 2 and then for my smaller triangle, for my smaller square, and for my bigger square, it's 4. Well, it's going to be 2 to 4, 2 to 4, 2 to 4, 2 to 4 for every side. So that would, they all would reduce to 1/2. So this green square is 1/2 of the red square, but sides are 1/2 the length. Same thing with these other shapes. So if you're given, you have 2 regular hexagons, then you already know they're similar. You don't need to do any more work in testing them. And just also remember that those theorems we talked about, side, angle, side, similarity, side, 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 and angle, angle, those only work for triangles. It's not going to work for these guys that have more sides, because if all I know is side, angle, side, these sides could be doing a whole mess of things and the shapes won't be similar. So just keep that in mind that that's only true for triangles.